In the previous segment, we introduced the ideal gas law, right? And the ideal gas law related things you might measure for a gas. So it related pressure, volume, and temperature, and the number of particles for a specific gas. Now I want to talk in this segment about some applications of that, about some processes where one or more of those things might be held constant. And some of these have some specific names, and so there is a bit of sort of memorization, bookkeeping, organization, as opposed to just logic in this segment. So there's sort of some trivia to keep track of, I suppose you might say. So checking out the PowerPoint, we can represent the state of a gas by a point on a PV diagram. What is a PV diagram? It is a graph of pressure versus volume. So we put pressure on the vertical axis, volume on the horizontal axis. It turns out to be a very useful way of representing information. And so then we can, by representing that point on a PV diagram, then we can represent a process as some path on this diagram. So for example, if this gas moves from an initial point here to a final point here, then we could represent it as a little arrow, a line connecting the initial and the final points in the PV diagram. Notice that in this particular process, we see a constant volume and a changing pressure. Now, in this case, we're imagining we've got a container of gas, and we're manipulating this container of gas somehow. So, going back to the ideal gas law, we see that PV equals nRT. What we can do is we can bring that T over to the other side of the equation. PV over T equals N times R. And so that means that, well, R is a constant, right? R is just a number, we look it up. And N is the number of moles. And that means that if we have a closed container with a fixed number of particles, that everything on this side is constant. That means that PV over T never changes. It never changes. And so that allows us to write that PV over T at one point in an ideal gas process is the same as PV over T at a different point in a gas process. That's often represented like this, as shown in the PowerPoint. P final, V final over T final equals P initial, V initial over T initial. For historical reasons, in your chemistry class, you might have learned this in bits of pieces at a time. Like if volumes are constant, it's P over T equals P over T, and they have different names, Charles and Boyle's law. I don't know. In physics class, it's just PV over T. If one of them is constant, we cancel it out, and we're left with the remaining variables that change. For example, in this case, we have a constant volume process. So my VF is equal to my VI, and they would cancel, and I'd be left with P final over T final equals P initial over T initial. This constant volume process has a special name. It is called an isometric or an isochoric process. Two different ways of describing a constant volume process. An example of this process might be shown here. I have some gas at some initial lower pressure. I add some heat, the pressure goes up. That's an isometric process, and you can see that it is a vertical line on our PV diagram. We could also have a horizontal line on our PV diagram. In this case, we're moving from some lower volume to some higher final volume at a constant pressure. This is called an isobaric process. Bar, that's a root for pressure type things, barometric pressure. So isobaric is a constant. Iso means constant, baric relates to pressure. Constant pressure process, isobaric. How might you accomplish this? Well, you might have some container of gas with a movable piston. Since the piston is movable, the pressure on both sides is equal, and we have a constant pressure situation. Since the piston is movable, and the total pressure on the exterior is constant, then this movable piston ensures that we always have the same pressure on the inside of this container. By adding some heat, I can increase the volume. An isobaric process. An isothermal process is same temperature process. Now, we might do that by submerging our piston in a water bath that's kept at a constant temperature. And if we do this process very slowly, then any heat that is generated by doing work on the gas will flow out into the water. maintaining a constant temperature within the cylinder. Isothermal processes are shown by these lines right here. These are hyperbolas, and we call them isotherms. An isothermal process is a constant temperature process, and an isotherm is a line of constant temperature. So here we see an isothermal process where we move from an initial state to a final. Here's an example. A sample of gas is in a cylinder with a movable piston. The force on the piston can be varied, altering the pressure and volume. A sample of gas is taken from an initial state to a final state following a curve shown here. The final temperature is what? Is it at a higher temperature? Is it at the same temperature? Or is it a lower than the initial temperature? Why don't you try and figure this out, and I'll see you on the other side. All right, well, here's our ideal gas law applied to constant number of particles. In this case, we have a constant volume, don't we? So this is an isometric or an isochoric process. My volumes cancel, and therefore I could solve for my final temperature. Notice I get my final temperature is equal to P final over P initial times T initial. Notice that the pressure is increasing because P final is greater than P initial. So we have a greater pressure final than initial, therefore this is greater than 1, therefore my final temperature is higher than my initial temperature. You know what, we didn't have to go through all that rigmarole. We actually could have just looked at this graph and answered the question. How? Well, let's look back at our isotherms. Notice that our isotherms increase in temperature as you move away from the origin, which means that any horizontal line moving to the right has an increasing temperature, and any vertical line moving upward has an increasing temperature. Here's another one. A sample of gas is in a cylinder with a movable piston. Same scenario, but now it's following this different path. Is the temperature increasing or decreasing? Well, let's just jump to the exciting conclusion. The temperature is decreasing, isn't it? Because I'm getting closer to the origin. Right? If I'm on a horizontal line, I'm moving to the left, then I am crossing isotherms to get to a lower temperature. The higher temperature isotherms are always farther from the origin. Here's a quick example. I think there's a couple of pitfalls that I can demonstrate how to avoid here. A snorkeler takes a deep breath at the surface, filling his lungs with 4 liters of air. He then descends to a depth of 5 meters, where the pressure is 0.5 atm atmospheres, higher than at the surface. At this depth, what is the volume of air in the snorkeler's lungs? Okay, well, what kind of a process is this? Is there any of these things that remains the same? Well, if we assume that air very quickly comes to body temperature, and that 4 liters is at body temperature, let's make that assumption, because I don't know how we can solve it if we don't. Let's make that assumption, and in which case the temperature just stays the same as he goes down. Okay, so my temperature stays the same, so those cancel. So solving for V final, we get V initial over P final. What's the initial pressure? Is it 0? It's not, right? We need to use the absolute pressure. The gauge pressure is 0 when he's at the surface. But that means that the absolute pressure is 1 atm. And my initial volume is 4 liters. My final pressure is 0.5 atmospheres higher. So that's 1.5 atmospheres. And now I'm ready to run my calculator. It's just 4 divided by 1.5. 2.67. Okay, and notice the unit is liters. How do I know that? Well, my atmospheres cancel, and I'm left with liters. Okay, so things to watch out for. Using absolute pressure, for sure. Did I pull a fast one on you with the units? Right, before I'd said, we got to make sure our pressure's in pascals and our volume's in meters cubed. Well, notice that if I set these two things equal to each other, as long as whatever my units are over here match my units over here. It's all going to work out. The big difference is temperature. Temperature's got to be in Kelvin, right? Because Celsius and Fahrenheit, it's an additive conversion, not a multiplicative conversion, right? Similarly, this has to be the absolute pressure. You can use whatever unit you want, but it has to be the absolute pressure. So it has to be the absolute pressure in PSI or pascals, or in this case, atmospheres, right? And so then you can see that whatever unit of pressure I use, it cancels, and whatever unit of volume I use, that's what I end up with here. Now be careful when you have to watch out for that and always use standard units, is if you're using the form like this, right? Because there are units in the R right here, you have to be sure that the units in these other values match the units in your R. Lastly, an adiabatic process is a process during which Q is 0. In other words, there's no heat transferred into or out of the system. Example of an adiabatic process would be some sort of a process within a well-insulated container. Another example of adiabatic process would be something that happens very quickly, and so there's just not time for heat to flow into or out of the system. In a later segment, we'll talk about mechanisms of heat transfer, but they all mostly take a little bit of time. And so an adiabatic process, we can often model processes as adiabatic if they happen over relatively quick time scales. At any rate, the point is that adiabatic means Q equals 0. No heat is transferred into or out of the system. A couple of points to remember is that an adiabatic expansion lowers the temperature of a gas, and an adiabatic compression raises the temperature of the gas. So here I have this lighter, and this lighter is full of compressed butane. And obviously if I start it on fire and hold my hand over it, it feels hot. However, if I just press the button down and hold my finger here, it actually feels slightly cool. And I can feel it even more if I put it to my lip or somewhere where it's a little more sensitive. I can feel it for sure. It's cool on my lip. Why is that? Well, inside the lighter, this gas is compressed. In fact, it's in the form of a liquid inside the lighter. As it expands, as it leaves the nozzle of the lighter, it expands very quickly. So quickly that there's not time to exchange heat with the surrounding air. So this is an adiabatic expansion. The gas feels cool as it comes out. You can do a similar experiment yourself. If you go like this and blow on your hand with sort of pursed lips, well, the gas expands as it leaves your mouth, right? You're creating a slightly higher pressure in your mouth. And therefore, when it leaves your face, it leaves your mouth, it expands, and adiabatic expansion cools the gas. This feels cool on my hand. And even if I blow very softly, it still feels cool on my hand. It's an adiabatic expansion. Compare that with this. That feels warm on my hand. Why? Because it's coming out of my body. It's warm, right? So again, an adiabatic expansion lowers the temperature of the gas, and adiabatic compression raises the temperature of the gas. An example of the adiabatic compression of a gas is when you pump up your bicycle tire. You just do that for a few times, and then you reach down and you feel the valve, and it's going to feel a little bit warm. Once you compress that air and put it into the bicycle tire, it gets hot. It turns out this is part of why airplanes get so hot. Airplane companies spend a lot of money on air conditioning. Why? Because they're bringing in low pressure air from the outside, they're compressing it and bringing it inside. When they do that, the temperature of the gas goes way up. Another example of an adiabatic compression raising the temperature of a gas.